All right, we're going to talk about inverse functions. So we are going to find inverse functions informally. We're going to verify that two functions are inverses of each other. We're going to graph them, determine that they are reflections over the line y equals x, which we'll talk about. We use the horizontal line test to determine if they're one-to-one, and we'll find them algebraically as well. So this is what the book says about the definition of inverse function. If I think two functions are inverses, if I do the composition for both of them in both different directions, so f of g of x and g of f of x, and I get x for both of them, then they're inverses. Okay, we can write that in this notation as well. F of f inverse will give you x, and f inverse of f will give you x. Let's do an example then. Here's a line, y equals 4x, or f of x equals 4x, and I want to find the inverse, and then verify that f of f inverse gives you x, and also that f inverse of f gives you x. So why don't you guys go ahead and try this one? So I'm going to take this original function, I'm going to call it y equals 4x, just because I like to work with y better. Now what you do to find the inverse is you switch x and y, gives you x equals 4y, you divide both sides by 4, and you get y equals x over 4. Now, I'm going to write this as f inverse of x instead of y, because that is the inverse. So this was f of x, and I switched x and y, and I got this as my inverse. Inverse is x over 4. Now, this function right here, you can tell that they're inverses of each other if you do the composition. So f of f inverse gives you, take this function, stick it in, you get 4 times x over 4, which gives you x. And also f inverse of f gives you, I'm going to take f of x and stick it into this function, so it'll be 4x over 4, which gives me x. So this tells me that they are inverses of each other. Also, if you graph these lines, y equals 4x is the line that goes through 0, has a slope up 4 over 1, so that line looks like this. And then this inverse, x over 4, looks like this in red. It has a slope of 1/4, so it goes up 1 over 4. So what you notice is that these two lines right here are reflections over this green line, y equals x. So this is the line y equals x, and inverses are always reflections over this line. And the reason why is because all an inverse does is it takes an ordered pair like this pair 4, 1, and it switches the x and the y, so that this would be the point 1, 4. That's all an inverse does. It takes every point and switches the x and the y. That's all an inverse does. It basically is something that undoes a function. So if you do some operation, so you divide by 2 and add 4 to every single point, that's what your function does, the inverse will undo that, which is obviously very helpful for like computer programming when you want to undo something. So all an inverse does is switch the x and the y. And that's how we found our inverse in the first place. So let's go through some more of this. All right. So I talked about this reflection of the line y equals x. No matter what the function looks like, its inverse will be the reflection image over the line y equals x. All right. So here's two more then. Here's a line, and then I've given you the inverse. You could graph both of these to see that they are reflections of the line y equals x. So this line f of x is 2x minus 3. It's got a y-intercept of negative 3, and it's got a slope of up 2 over 1. Looks like this. This function right here, if I distribute the 1/2 to both terms, is 1/2 x plus 3/2. It's got a y-intercept of 1.5, so I'll do this one in green. And it's got a slope of 1/2, so it means it goes up 1 over 2. Up 1 over 2. It looks like this. All right, these should be reflection images over this pink line. So this line y equals x, these lines should be reflected over to each other. That means they're inverses. So here's some points that are on both these lines. You can see that like the point negative 1, 5 is on the original function, and then you can switch these x and y and see that the point negative 5, negative 1 is on the inverse. So you can see that what inverses do is they switch the x and the y's. Okay, next is the horizontal line test. We use the vertical line test to tell if functions were actually functions, but we're going to use the horizontal line test to determine if a function has an inverse that is a function. So, for example, we're going to call this 1 to 1, but for example, let's take a look at y equals x squared. Y equals x squared is a parabola that looks like this. This function clearly does not pass the horizontal line test, which means that its inverse is not a function. And I think that would make sense too if you were to graph this line y equals x right here and reflect this function over, you'd get this function in blue, which looks like this. So if you reflect this parabola over the line y equals x, you get this, and you can tell this does not pass the vertical line test. Okay? So what it means for a function to be 1 to 1 is it would pass the vertical line test, and every x is going to have exactly 1 y. All right, so this blue function is not a function. This blue relation is not a function because it doesn't pass the vertical line test. So if you look at this table of values from the parabola, here's the original function. When you switch x and y for the inverse, you can see that this point 4 would have the same x value with 2 different y values, which would make it not a function. Okay. What about this function, x cubed minus 1? This does pass the horizontal line test, therefore this is a function. So the inverse of this is a function because this does pass the horizontal line test. So if you graph the line y equals x, you can try to draw a rough sketch of what this would look like. It would look something like this. This is going to be bad, but I'll try. This blue function does pass the vertical line test then. So if this is the original function, this would be the inverse. All right, so here is another one. Let's find the inverse of this. To do that, we're going to switch x and y. So I'm going to call this y for f of x. And now I'm going to switch x and y, so I get x equals 5 minus 3y over 2. Now I'm going to solve for y. So I'm going to multiply both sides by 2. This gives me 2x equals 5 minus 3y. Subtract 5 from both sides. I get negative 3y equals 2x minus 5. Divide everything through by negative 3. You get y equals negative 2/3 x plus 5/3. So this is our line, and this is the inverse. Okay. Now we could graph both of these and make sure that they are inverses, to make sure that they're both reflected images over the line y equals x. We could also test to see that they're inverses of each other by taking the original f of x and plugging it in. So we'd have f inverse of f of x. If we do this composition, you'll get x. And if you do the other composition, you'll get x. Okay? Now I'll graph both of these real quick in the calculator. Alright, so I've got the second one plugged in right here, 2x over negative 3. I put the negative sign at the bottom, it doesn't matter. And the original function, 5 minus 3x over 2. Now the calculator doesn't, one of them is a red line, the other one's a blue line. And I also graphed line y equals x, which is the green line, to show that they're reflection images of each other. It doesn't look like, it doesn't look the best because it's not going to give you a this calculator is not a square window, it's more of a rectangular window, just by the design of the screen. So like, it doesn't look perfect, but this red line is a reflection image over the green line, and that point will land in the blue line. And if it was a perfect square window, which I don't know, maybe I can even do. Yeah, I can. If you do a perfect square window, then you'll see it more obvious, where this point is reflected over. Back what you learned in geometry is that if you connect a line between these 2 points, this is a right angle and these distances are equal to the reflected image. So all of these points on the function are reflected over the line y equals x and will be on the inverse function. All right, I hope this helps.